Let's establish a parallel between gravitational forces and electric forces. When we look at a gravitational force, it depends on three things. It depends on the mass of the first object, the mass of the second object, and the distance between those two objects. When we look at an electric force, there is a different constant that we are looking at, the electric force constant. It depends on the charge of the first object, the charge of the second object, and the distance between the two objects. How are these two equations similar and how are they different? Both of them have this dependence on an r squared value, this inverse square law. So if we double the distance between two charges, the force between those two charges will drop to 1/4 of the value, correct? If we double the distance between two masses, the force between those two masses will drop to 1/4 of the value. Triple the distance between two charges, that'll be 1/9 the force. Okay. How else are they similar or different? They depend on a characteristic of the two different objects. This one depends, gravitational force depends on the masses of each of those objects. Increase the mass, you increase the force. Electric force depends on the charge of those two objects. Increase the charge, increase the force. Knowing what you now know about electric forces, can you explain why gravitational force is only a positive force, but the electric force can either be a positive force or a negative force? Imagine something with negative mass. We can't imagine something with negative mass, can we? Here we've always got positive values for mass, therefore this one would always be positive. Here you can have a positive charge or a negative charge, and that would result in a positive force or a negative force. But what does that do? Think again about gravitational forces. Gravitational forces always do what? Near the surface of the Earth, gravity always pulls things down. Always pulls things down. On a larger scale, gravitational forces are always, starts with an A. It means good looking. They're always attractive. Electric forces can either attract two objects or repel two objects. You know I messed this up. Gravitational forces, we've always left it out, but it's actually a negative force because of that attraction. A negative force is a force that pulls things together. A positive force would be something that pushes them apart. So let's take this one step farther. If we talk about a gravitational force near the surface of the Earth, then we would talk about the mass of an object near the surface of the Earth and the acceleration of gravity near the surface of the Earth. If we talk about electric forces, in terms of just one charge, not two charges, but just one charge, then it would be that one charge times a value known as the electric field. Those have similarities too, don't they? Now you're just looking at a single object and its characteristic mass, or a single object and its characteristic charge. A mass in a gravitational field, a charge in an electric field. Let's put a definition on that then. In general, an electric field is the space around a charge where an electric force can be felt. How do you calculate a value for the electric field? If we go back to this one, the acceleration of gravity here is everything but one of these masses. That would be the gravitational force constant, one of the masses, and the distance between those two masses. How do you calculate the value of an electric field? It's going to be everything up here in the electric force except one of the charges. The electric force constant, the other charge, and the distance between them. So how do you calculate the magnitude of an electric field? Given the value of a charge and given the distance from that charge, it's really not very hard at all. Units will be important though. That's exactly what this says. Rearrange this thing a little bit here, and we get, how do you get that charge over there? Divide that by the charge. This is in newtons, this is in coulombs. The more charge we bring in, the more force you're going to feel. If you have a positive charge, the electric field around a positive charge is always directed away from that positive charge. The electric field around a negative charge is always directed towards the negative charge. How are we going to remember that? Easiest way to remember it is throw some positive charge in here, and what's it going to do? A positive charge next to a positive charge, what are those going to do? They're going to spread out. They're going to repel. They're going to go away. So this gets pushed away in that direction. Put a positive charge near a negative charge, and what do? They attract each other. So the positive charge is going to get drawn into a negative charge. So these electric field lines they describe what happens to a positive test charge. We've got one in there. Let's put another positive charge in, and another positive charge in, and another positive. Let's put a whole lot of positive charges in here. What will all that extra charge do to the value of our electric field? Will the electric field value increase, decrease, or stay the same with more charge? 7 times as much charge, the electric field will be 7 times stronger. How do we signify with electric field lines that this force is going to be, or that this field is going to be 7 times stronger? You indicate a stronger field with more field lines. Now, one more thing about that. If more field lines means that the electric field is stronger, will this charge feel a stronger force closer to all that charge or farther away? You know that from this electric force equation. The closer you get, the stronger the force the charges are going to experience. But just looking at the field lines, how do you know, looking at these field lines, that there's going to be more force closer in? Where the lines are closer together, there will be a stronger force, or the field is stronger. We could go extreme on this, not changing the angle of any of these, just showing, look how far apart those field lines get. That positive test charge there is going to feel less and less force because the field lines are spreading out, spreading out, spreading out. Let's put a positive charge over here and a negative charge over there. And I just showed you, positive charge pushes away, negative charge pulls in. But let's put them together. There will be, this one will push away, that one will draw in. This one pushes away, that one draws in. But it pushes away in this direction too and draws in over there. Can you expand this out to figure out what's this field going to look like, here, 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 on both sides, on the left side of the positive charge, on the right side of the negative charge, up higher and down lower. So if we add some more to this drawing, then things go, I actually don't have enough space here. There you go. A few more in here. That's what the electric field looks like around a positive charge and a negative charge. And this is where I'd like you to go to that simulation I just showed you. What I just showed you is known as a dipole. And this motion of particles, each one of these little white dots is like a positive charge. Can you identify on this simulation which one of these two charges is the positive charge and which one is the negative charge? The one on the right is negative. Why is that? Because it's pulling in, and the one on the left is positive because they're getting pushed out. Can I draw on this? Nope. Oh yes, I can. Positive and negative. And then when you look at those field lines, it shows exactly what you just drew. Just looking at the field lines, you can't identify which one's positive and which one's negative, but you can at least describe what path a particle would follow in general.